Chapter 15, Energy and Chemical Change. We are going to join 15, Section 1, 2, and 5, along with Chapter 16, Section 1 and 2 together. So 2 portions of chapters. Not too bad. You'll see. Energy and chemical change. So what's energy? It's the ability to do work and produce heat. There's 2 different types. You learned this your freshman year. Kinetic and potential.
And 8th grade.
And 8th grade, wow. Kinetic and potential, so we're not going to go into a ton of detail. If you need to review those, go get your textbook.
See me.
Law of conservation of energy. The energy can be converted from one form to another, but it is neither created nor destroyed. So you could be in kinetic, you could be in potential, but you can't lose any. Your chemical potential energy is the big portion that we need to know for chemistry class. All right, since we need to know chemical potential energy for chem, definition: energy that is stored in a substance because of its composition. So propane, we use that to heat our houses or to cook things or do lots of different things. Lots of carbons, hydrogens, oxygens that we can break bonds. We can produce energy once we break those bonds. But propane just sitting there is just propane gas. Yes. So it has the potential to do work for us or create energy for us, but by itself it's very stable and won't do anything.
So all of the potential energy comes from the amount of bonds and the types of bonds that you can break and how much energy you would get if you break them.
Excellent. Measuring heat. Heat is the energy in the process of flowing from a warmer object to a cooler object. Since I'm the cold-hearted, evidently it would be moving from her to me. This is called Q. Heat is Q. You're going to see this in your equations coming up. So heat is Q, little q. Heat is measured in joules or in calories. 1 calorie is equal to 4.184 joules. And 1 nutritional calorie, and notice this one has a capital C,
yes,
and the one behind it, the 1 calorie for the joules, is a lowercase c. They are 2 very different things. So 1 nutritional calorie, how much you're actually eating in, is equal to 100 energy calories.
1,000.
Darn it. 1,000 energy calories.
Because it's a kilocalorie.
Or 1 kilocalorie. Because I can read today. All right, so your nutritional calorie is different than a energy calorie, only because 1 is equal to 1,000 of the little guys.
Right.
And then that 1,000 would also be equal to the kilocalorie. Make sure you're just paying attention to how the calorie is written, lowercase or uppercase, and it'll give you a big difference in what you need to do. All right, specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So how much heat is going to be given off? How much do we need to put in to raise it? All that wonderful things. So your equation for heat, here's that little q. Little q is equal to C times M times delta T.
Yes.
The very next sentence, we're going through it.
Okay.
C is your specific heat constant. So depending on what substance you're talking about, you are going to look on a chart, which we're going to give you as your new little cheat sheet, and it's not on your old one. We have to fix that one. We'll give you a new one. There's a whole chart for every single substance that you are talking about. You're going to look up specific heat of that and plug it into C.
Or it'll be given to you in your problem.
Yes. Oh, that'd be a nice thing to do then.
Yeah.
You've got the mass of whatever you're talking about, and then delta means change in, and capital T is your temperature. For this chapter, we're going to be talking about Celsius, and we can leave it in Celsius. Unlike your gas chapter where you had to move everything to Kelvin, this one's really nice to you. You can just leave everything in Celsius and be nice and happy. Our little note as to why specific heat's important. Water has a high specific heat, which helps regulate the Earth's temperature. So we don't get too warm, we don't get too cold, and all that fun stuff.
Yes, if you think about how much of the Earth is actually water, that's what helps regulate our climates, our temperatures, so we don't have extremes.
We like to think we have extremes in Ohio, but what are you going to do? All right, so let's do a problem. We're going to use that equation from the last slide, our Q equals, and we have a silver bar. So a silver bar with a mass of 250 grams is heated from 22 degrees Celsius to 68.5 degrees Celsius. How much heat does the silver bar absorb? So we want to find our Q. Our mass is 250 grams. And from, I should have put it in the problem, but the chart in the book or cheat sheet, you're going to have C for this is 0.235. So that's the specific heat of silver. And you are going to multiply it by the difference in the change in temperature, which means you are going to take your 68.5. Now, change means final minus initial. So you got to take take the 68.5, subtract the 22, and then you just plug it all together, and you're going to get 2,730 joules of heat energy.
Okay, now notice that this is in the amount absorbed, and so it's going to be a positive number. If you have your final temperature that's lower than your initial, then you're going to end up with a negative Q.
Okay.
So you could have a positive or a negative there.
All right, awesome. Now, where the joules comes from, you've got your specific heat has
Yes.
a bunch of labels in it, and that's where we canceled everything out, and we ended up with our joule to be left. All
Okay.
right, pretty
Got
good? Okay. Let's talk thermal energy. Thermal energy is the energy of a system due to the movement, the translation, vibration, and rotation of its particles, how much they're actually moving against each other. Thermal energy of an object depends on the amount of matter present, the temperature, and the chemical composition, so what it's made up of, how hot it is or cold it is, and how much of it you actually have. Some materials require little energy to change their temperature, and other materials require great deals to change their temperature by the same amount. Just depends on what you're actually talking about. Everything's got its own little set of rules.
Think about metals. Metals require very little energy to heat them up because they are good conductors, and water, it takes a lot of energy to heat them up, so they have very different specific heat.
Excellent. That is the end of section 1.
Awesome. Let's go to 2.
All right, section 2. We're going to talk about a calorimeter, which you used your freshman year. You started heating up some Cheetos. Is that what you used?
We use Cheetos and marshmallows.
Oh, yum. That's
We've
a good combination.
We don't have a fancy calorimeter. Remember, it's like styrofoam cups.
Yeah, well, what do we use? How do we know how many calories are in our actual food? So a calorimeter is an insulated device used to measure the amount of heat absorbed or released during a chemical or physical process. The picture you have here is also in your book if you can't really read it very well. This is called a bomb calorimeter because everything's encased, and they're going to heat up the water, and they're going to stir the water, and then they're going to heat up the stuff that's inside the little chamber in the bottom inside, and as much as they can heat it up, the temperature is going to raise or fall or whatever is going to happen, and you basically are measuring it, right? Okay, so energy transfer. Specific heat values can be used to calculate the thermal energy change, the temperature, the initial, final, or change in, or the mass of a material in the calorimeter. Oh,
So that same equation that we used before.
That's good. All right, because we're going to need that. All right, let's talk about endothermic and exothermic. Here we've got 2 graphs. When your little q is negative, the reaction is giving off heat, and it's called an exothermic reaction. Here we have your chart. It has potential energy, and it has your reaction pathway, how you go from your reactants to your products and what actually happens. Now in here it says your activation energy just means you're going to put some energy in for it to actually start going.
Right.
And once it starts going, you're good. You can keep it moving.
Right.
And then it'll drop. That means it's actually given off a bunch of energy to get all the way to the bottom there. Activation complex we'll actually talk about in the later part, so I'm going to let that go. And we're just going to compare right now to the endothermic. When Q is positive, the reaction is absorbing heat, and it's endothermic. So in this one, your reactants were at the bottom, you went up the curve, and your products were actually still really high. So that means you actually had to take in that energy, and so your energy is higher in your graph.
Yes.
Not too shabby, huh?
Nope.
All right. Math problem. You ready?
Oh boy.
It's kind of a big one.
Yeah,
It's not hard. It's just a couple steps.
Okay.
So using the calorimeter contains 195 grams of water at 20.4 degrees Celsius, a 37.8 gram sample of unknown metal, so we got to figure out what this metal is heated to 133 degrees Celsius and placed into the water in the calorimeter. Heat flows from the metal to the water until both reach a final temperature of 24.6 degrees Celsius. What is the specific heat of the metal?
Okay.
So what we have to do is we have to use our Q equation, and we have to figure out what our change was for our water.
Okay.
What was our heat for the water? So we're going to set it up, and I have it all written down over here because it's...
So we're looking for Q of water?
Yeah, and you're going to want to kind of stay over there because then we got to write more later. So the first thing we need to do is find Q of water when using the calorimeter. So we've got 195 for that. Your C for water is always going to be 4.184. And your change in temperature was the 24.6 minus 20.4.
Okay.
So once we plug all that in, we can find our little Q for water is 3,430 joules.
And it is positive.
Positive, yay.
Okay.
All right.
Okay. All right. This value is a positive up here. Where is my pointer anyways? Okay, there we go. This is a positive because this absorbed. Now we know our Q value, so we're going to bring it down here. And because this one is releasing heat, it needs to be a negative value.
All right.
Okay? And then technical difficulties, but I filled in your other things for you. You have a mass of 37.8, and then you have an unknown C value. So we are solving for C, and this is your final temperature, 24.6, minus your initial temperature of 133.
Okay.
Because it cooled down from 133 to 24.6.
All right, so we got to get C alone. So that means we have to get rid of our 37.8.
Okay. All right. Let's see. We do
negative 3430 divided by 37.8 times 108.4.
But it would be
That's your
negative.
temperature. Yeah, negative. This is why I keep you catch me on everything. All right, plug, and you get 0.84. And since it's a C value, you've got a lot of labels.
Okay.
Joules divided by gram times Celsius. You've got this.
I remember this from college.
Yeah, there you go. All right, so section 15.5.
Yes.
Not much here. Spontaneous reaction. Not a spontaneous little combustion where you've seen this on conspiracy theories where people just instantaneously
really
catch
crazy.
on fire and yeah. Spontaneous process in chemistry is a reaction that occurs without any outside intervention. So you've got your rust. You've got your oxygen and your iron from your iron oxide that just reacts and makes your rust. Some spontaneous reactions do need an input of energy to start it, such as you lighting your Bunsen burner. You have to at least give it just a little spark. As soon as you've got that spark, it's going. And then you don't need to put anything else into the process. It's already started. Another one, you may not have to actually put in the energy. It just needs the change in temperature, such as ice melting. This is a spontaneous process. You're not standing there doing something to it. You just have the temperature change and ice will melt. Or if it gets too cold, it will form ice. So moving through your physical changes, all that fun stuff. Entropy. Entropy is known as S. It is the measure of the number of possible ways that the energy of a system can be distributed, because I can read today. And this is related to the freedom of a system's particles to move and the number of ways that can be arranged. Whew. So, easy way. The more the particles can move around and bump into each other and move away from each other, you're going to have a high entropy.
So gases.
Gases. If your particles are stuck very close together and can barely move,
solids,
you're going to have a low entropy. Entropy is the freedom. The more you can move away and bump into each other, the bigger your entropy. So, there are 5 factors that can increase or decrease your entropy. Changes in state. Entropy can increase when a solid changes to a liquid and when a liquid changes to a gas, so moving through your states of matter. Because these changes in the state result in freer movement of the particles. Dissolving a gas in a solvent. When a gas is dissolved in a liquid or a solid solvent, the motion and the randomness of the particle is limited. You're putting it into a confined space. Ooh, nice. You're going to take a gas and you're going to try to pump it into this liquid. Well, there's already particles of liquid in here. So those gas particles really can't move a whole lot. So you've actually decreased your entropy because they're stuck in here. They can't move as free as what they once did.
I have a soda stream and we add carbon dioxide.
Nice.
And it's doing just that.
Excellent. All right, number 3, changes the number of gaseous particles. When the number of gaseous particles increase, oh, thanks. The entropy of the system usually increases because more random arrangements are possible. So if you put in more gas stuff, gases can move, they can bump, and you're never going to find where that gas particle typically is.